Okay, any question before the class? Okay, let's get started. We have finished the single cycle CPU design last time, and the question is, what is single cycle CPU? Single cycle CPU. Each instruction is executed in one clock cycle, right? So in this example, addition instruction is executed in this clock cycle. Clock cycle number 1, and next instruction, LW instruction, is executed in clock cycle number 2, and this one, number 3. Then the question is, that CPU, is it single cycle CPU? Think about that. And why? Why there's single cycle CPU? Confusing, right? Confusing or not? I can see any of your face. So I'm confusing. If you are confusing or not, I'm confusing. Is it single cycle CPU or not? So to figure that out, right? To figure it out, you have to draw this timing diagram. Okay. So let me draw this timing diagram very carefully. Okay. Assuming that CPU is executing these 3 instructions. Okay. Then addition instruction. Okay. Each instruction started from each instruction starts from program counter, right? Program counter is providing memory location, then instruction is coming in, then decoding execution. So instruction execution gets started from this program counter. So let me draw this program counter, PC output, right? That output, this flip-flop output, that point. Okay. Okay. So can I do? Okay. So let me do this. Add insert what? Insert. Okay. So let me PC program counter is this place. See which color? This one? No. This one? Okay. Okay, that place, PC. Okay. So program counter is let's say program counter is initialized to 0. It starts from 0. Okay, I'm drawing this very carefully, considering the delay, flip-flop delay. Right? So 0. Some delay, right? Delay. Okay. Then program counter will be incremented by 4, like this. Then 8. Okay, 4 and 8. Then check out then this signal. Okay, what signal? This one, instruction. Okay. Instruction. Okay. Instruction. Instruction is coming like this. Program counter is provided to instruction memory. So after a little bit of delay, memory access delay, right? Instruction will be available like this. So that delay, right? You are providing program counter, then after that is memory delay, mem delay. Okay, then addition instruction is provided from memory. Okay, and location 4, LW instruction is coming in, right? X5, 4, X3. And location 8, we assume that instruction is placed. So BQ, X3, X5, this label. Okay, and then which signal do you want to observe? Probably important thing is about this one, OP1, source OP1. First input to ALU. Okay, first input to ALU about this. Okay, source 1, then source 2. This one, second input to ALU, source 2. And we want to observe that ALU output, because that is important signal, right? This ALU out, about that. And probably for memory access instruction, you want to check out this signal, mem out. How about that, mem out? Okay, this mem out signal. Okay, how about that? Okay, so source operand OP1, source OP1, source OP2. So for that instruction, source operand X0 first, and second is immediate 12, right? So that will be available after some delay, right? So register file access delay. You have to access the register file to get first source operand, and you need go through this block, sign extension logic and multiplexer to get second source operand. So after some delay, right? After some delay, source operand will be available like this. Okay. So first source x0 is which 0, right? And then after sign extension and multiplexer delay, that constant 12 will be available. Okay, then addition instruction, right? So control logic is generating addition control signal for ALU. So ALU out will be, after providing this two source operand, right? Two source operand after some delay, right? Some delay, ALU out, 0 plus 12, 12, right? That will be available like this. Okay, then at the rising, right? At the rising edge, this rising edge of the clock at this point in time, right? At this exact point in time, okay, register file will be updated, right? So location X3. So RT, if you destination DST destination destination register, right? DST, let's call this destination register, which is what? X3. And X3 will be available after getting this instruction. Control logic, right? Control logic can extract a destination field from this machine code. So that is taking some time. So destination number, in this case 3 will be available after some delay, right? This one is control unit delay. Control unit is extracting. It is very small, just extracting that number, right? And at the rising edge of the clock, the rising edge register file, okay, will update this data to that location. So single cycle CPU from instruction execution, this clock cycle, right? Clock cycle number 1, instruction fetch started, then register file is updated at the end of this clock cycle. So single cycle CPU, right? Addition instruction gets executed in one clock cycle. Does it make sense? I'm confusing. Okay. Okay. Chatting. Okay. And then let's execute second instruction, which is memory read instruction, LW, right? Same thing is happening, right? So you got instruction, then source operand, right? Source operand is what? First source operand x3. X3 happens to be what? Happens to be 12, right? That instruction updated x3. So 12, right? Happens to be 12. And the second source operand to ALU is coming from that immediate sign extension immediate, which is 4, right? 4. And then ALU will do addition operation, right? 12 plus 4, which is 16, right? So after delay, I'm drawing this very carefully, right? ALU delay. Okay. Then based on this memory location, based on that memory location, okay, based on that memory location, memory will be accessed. Okay. So data is coming out through that pass. So mem out. In here you have to draw mem out. Okay. So very crowded. Mem out signal. Okay. So let me draw mem out in blue. So after the memory access delay, right, you are providing this memory location, which is address. Okay. Then after some delay, the data will be available. Okay, data. That is mem read data. Okay, I don't know what it is. Okay. Then destination register is what? Destination X5 register. Okay. So destination. After getting this instruction, you can extract that destination field X5, right? So after control unit delay, destination register will be available like this, 5, right? 5. So then register file, right? Register file will update at the rising edge of this clock. Okay. That mem data, this data will be updated at that place, right? So location X5 register. So single cycle CPU from instruction fetch to register file update. Everything is done in one clock cycle. Okay. How about a branch instruction? Okay. Same thing, right? So here you got branch instruction inside the CPU, then source operand. In this case, what is that? X3, X5. X3 is what? X3 happens to be 12, right? From first instruction, 12. X5, X5 just got updated from previous instruction X5, but we don't know what it is, right? Because of memory data, right? So that is mem data. Mem, the data is right? Mem read data. So CPU will do subtraction operation, right? Subtraction to compare these two, right? So ALU output, that ALU out will be, I don't know, 12 minus mem data. Okay. So based on that, you can you can make that decision. What decision? Taken or not taken decision? Taken, not taken decision. Let's assume branch is taken. Okay, branch is taken. Then what should happen? If branch is taken, program counter should be updated with destination, right? Destination PC branch destination, which is computed, from that path, right? That adder, right? Adder, this adder, okay, is taking second input. Second input is what? Program counter, right? PC program counter of that instruction, okay, and then sign extended immediate. So PC plus sign extended immediate branch destination. So CPU will select that guy and update, program counter. So destination, right? Very crowded. Let me draw here. Branch destination, branch destination. So that is computed. That is computed with this adder. And think about the delay, right? Sign extension logic. You got instruction, you got branch instruction, and after sign extension logic delay, okay, L1 essentially this, this one is specified in immediate, right? Immediate. So sign extension logic delay and program counter, right? Program counter is available here, right? That is that, right? Program counter and sign extended immediate. Let me draw. Sign extended immediate, right? So roughly the same timing as that mem read data, right? So that is sign extended immediate, this label, right? L1. And this one, red one, will be added. This one will be added with that PC program counter PC plus the sign extended immediate. So after adult branch destination, okay, so branch destination, okay. If you add these two, then after some delay, after providing this data, some delay, branch destination will be available. Okay, so then at the rising edge of that clock, okay, program counter, that counter PC will be updated with this branch destination. So single cycle CPU from branch instruction fetch to program counter update, PC update. Okay, we assumed branch is taken, right? So instruction fetch to PC update, that is done in one clock cycle. So single cycle CPU. Does it make sense? Any question about this? Okay, then probably obvious question. Next obvious question is, what is this clock? Clock. This is clock, right? CLK clock. The obvious question is, what would be the operating clock frequency? Operating clock frequency of that single cycle CPU. Operating clock frequency. For example, our CPU is able to run at 100 megahertz, 200 megahertz. What is the number? Or 1 gigahertz? So what is the operating clock frequency? That would be obvious next question, right? Okay, let's talk about that. Where does the sound come from? Okay. So how fast the single cycle CPU is able to run? Okay, so we take this one as an example. Just simplified. I don't have this one doesn't have a jump destination logic. Okay, jump destination, branch destination, and PC+4 only, right? So I simplified it. Okay. Okay, Yunsu, can you please?
Can you hear me?
Mhm.
Yes. How fast is the single cycle processor? Clock cycle time. Frequency is limited by the critical path. The critical path is the path that takes the longest time. What do you think the critical path is?
Okay, thanks. You have to figure out critical path of that single cycle CPU. Critical path is the longest path, the longest delay path of an instruction execution. So in other words, from instruction fetch to the end, right? Fetch to the end, instruction fetch to the end, fetch to the end. What would be the longest path? Which instruction is incurring the longest path, and what is that path is? Okay. For that, to examine that, let's check out the data path. Those instructions are following. Okay. Which path should be which path should be taken to execute addition, add I, BQ, LW, SW instruction. Okay. Then one more thing you have to think about is you have to think about hardware component where clock is coming in. Which component is taking clock? Okay. Look at this. Look at this schematic diagram. By looking at this, program counter is the first one taking clock, right? That clock, program counter, right? Program counter, is designed with flip flop. Flip flop is taking clock as an input. And next one is what? Memory update, right? Memory update is happening at the rising edge of the clock. Okay, memory update also. Memory is also taking a clock, and the register file is also taking clock. So write operation, right? That X3 register update, X5 register update, that is happening at the rising edge of the clock, right? So for that, you need clock signal, right? So three components, okay? In this example, three components: program counter, memory for write operation, right? Memory update operation, write operation. You need clock and register file, okay? So you have to keep that in mind, right? Three components are taking clock as an input. Then let me draw. Let me use pen to draw the path. Okay, change animation, full screen. Okay, okay, okay. So let me use this one. Highlight, ink. Which one? For addition instruction, let me use this color for that addition instruction. Okay, addition instruction. So it starts from program counter, right? You patch it. You patch the addition instruction. Okay, this one, addition. Then instruction is coming in from memory. There is a pass. There is a pass, right? Instruction is taking, right? And then source operand, right? Sorry, this one, X5, X6, right? X5, X6 is provided to register file. Okay, And destination is X4, right? Destination X4, number 4. Then in response, a register file is providing source operand, right? X5. Then this time it is taking the pass, right? Then ALU is doing addition operation, and that output should be supplied to register file. That is the pass addition instruction is taking, right? That is the one. And add instruction is taking similar pass, okay, except second source operand is provided from that pass, right? Second source, right? Very similar, right? Then let me use blue. Okay, blue for branch instruction. Okay, starting point is the same from program counter. Right? Program counter branch instruction is provided. Okay, then first source, second source, right? Providing first source, second source, and then register file, right? Is giving data. Okay, X3, X4, and ALU is doing subtraction operation. Okay, based on that, you can figure out, okay, branch is taken or not taken, right? So assume that branch is taken. That is, longer, taking longer than not taken pass. Right? Then what should happen? Branch destination, right? Branch destination is computed by this logic, right? Adder. Adder is computing branch destination, program counter, okay, PC, then second source operand. Okay, PC plus sign extended immediate. Okay, that is updating program counter like this. So that is a pass. But so you have to be careful. To pick. So let me to pointer option pen. So, but the one thing you have to be careful is when you execute branch instruction, that pass, right? This computation, subtraction operation, subtraction operation, this one, and branch destination computation, 2. That is happening at the same time. We are talking about hardware, right? Hardware. So subtraction operation and branch destination computation is happening at the same time. Okay, so not separated delay. You don't have to add this one and 2 to compute, to figure out the longest, the delay, right? And then last one, let me use thin pen to seek. Okay, color red. Okay, so LW instruction, okay, memory read instruction starting from program counter, and then same thing. Instruction is coming in LW, okay. Then first source, second source, right? Same thing right here. First source operand X5 is provided, okay, and second source is taking that pass, okay, that pass, which is what 20 immediate, right? 20 second source. And ALU is doing addition operation to provide that memory location X5 plus 20. Okay, so providing memory location, then memory in response is providing data. Okay, and then should be supplied to register file. Okay, so by comparing these, three, last one, LW instruction is taking the longest path from PC, right? Same path, right? same path, but LW instruction, you have to access memory, right? This memory, right? That is critical, part. So differentiating the path, this path, from other paths, right? So store word instruction, think about that. Store word. Everything is the same as LW except what? Except you are updating memory, right? So that data is provided from this path, and memory is just updating data, this data at that location. That's it. Memory access, no register file update, no update. So by comparing these two, LW is taking longer path than SW instruction. Does it make sense? So let me change the option here. Start. So then, to critical path. Critical path is the path. LW instruction is taking. LW instruction starting from PC. LW is coming in, then source operand, memory location, okay, and data is coming in. That is the longest path. Okay. So from flip-flop to flip-flop delay, right? Critical path is flip-flop to flip-flop, right? That flip-flop. Flip-flop to flip-flop. Flip-flop to flip-flop delay. So in between these two, you have some, combination logic. D and Q, some combination logic. So that delay, we are talking about that delay. Okay. Which one is the longest time? Which one is taking longest time? From PC flip-flop to register file. Okay. So PC, that is program counter, and then there is register file. Okay. PC to register file. Not PC to this memory. Right? Not PC to memory, right? Store instruction is taking. That is shorter than LW path. Okay. So then, so little equation, formula equation. So critical path. So how long does it take that the time, right? How long does it take from that PC to register file? Okay, PC to register file to execute LW instruction. LW. To compute that critical path delay, look at this PC. Flip-flop delay. First one is flip-flop delay. Right? Hardware component taking time, right? All hardware components are taking time, right? Flip-flop delay, the time, this delay, flip-flop delay, right? And then memory delay. What is that? Memory delay. From instruction memory, you are reading, instruction, right? That memory delay. How long it takes to access, that instruction. Memory delay. Then what is that? Whatever is bigger, what is that? First one is register file read. This one. Okay. So if you think about that instruction, X3, register. First source operand is coming from register file. So register file access time delay or sign extension logic. This one, 4. Second source operand is taking that path. Okay. So you have to compare, okay, register file access and sign extension logic, including multiplexer. Which one is okay, sign extension logic. Which one is taking longer? So don't exclude this. Sign extension and register file. Which one is taking longer? I think register file, because it is big component compared to sign extension logic, right? Sign extension is very simple logic, right? And then multiplexer delay. Okay, multiplexer second source operand should go through this multiplexer, so mux delay. Then ALU delay. Right? ALU is doing addition operation. Okay, so heating, right? I think this building, right, is cold, so trying to heat the room, so some noise. First time running that machine. Do you hear that noise? Yunsu, do you hear the no noise? Okay, I'm on here. Okay, so ALU delay. Okay, ALU delay. ALU is doing, because ALU is doing addition operation, right? Addition operation. Where is that? Addition operation. Okay, and then memory access time, right? This data memory, TMEM, data memory access time. Then you have to go through this multiplexer, mux delay, and what is the last thing? Register file setup time. Setup time. What is that setup time? So I gave you analogy, right? So register file is taking picture. Flip-flop, right? Flip-flop is taking picture, right? So before you press the button, before you press the button, okay, before you press the button, the thing you are going to take, your friend, okay, your friend supposed to stand still. So sometime before you press the button, right? Sometime before you press the button, and after sometime after you press the button, your friend supposed to stand still, right? Right? You are pressing the button, and before and after, your friend supposed to stand still, don't move, right? If you are moving, then the picture is not clear, right? The same thing, happening, right? You are taking picture at the rising edge of the clock. You are taking picture of what? Of this data. This memory access data, this data. You are trying to store this data. And sometime before, sometime after, the data is supposed to stand still. Don't move, right? If you are moving, if you are changing, data is changing, then, I don't know what data would be stored in register file. So sometime before, sometime after. Sometime before, that is called setup time. Setup, okay? Sometime before, this one and two. Before, one, setup time, two, hold time. We call that hold. Okay, hold. Do not move, okay? Hold there. Setup and hold time. So trying to store to register file, do not, okay, your data should be ready. Sometime before I take the picture. Okay, sometime before. That is setup time. Okay. So data should be ready. So sometime before I take, before rising edge of the clock. So if you simplify this, we have two memory access, TMEM. So two TMEM. We are simplifying, right? And MUX, two TMUX. Okay, this MUX, two TMUX. And then you have to select either of these two. So we are selecting register file delay because it is, huge logic, right? Huge digital logic. So that will incur more delay than sign extension. So we selected this. Then we got this equation. That is clock period. Clock. Minimum clock, this one T, this time T. Okay. Minimum clock period. Minimum. Clock should be longer than this T min. Okay. That is a minimum clock period. So let's assume flip-flop delay is 30 picosecond. What is picosecond? Let me remove this. Sorry, picosecond. Picosecond is 10 to the power of minus 12. Minus 12. Super small, right? Minus 12. Right? 30 picosecond multiplexer delay, 25 picosecond ALU delay, 200 picosecond to get ALU output. Memory access delay, 250 picosecond and so on. Okay, so if you plug these numbers into that equation, then you got this number, 950 picosecond. That is a minimum clock period, right? Period. This one, period. 주기, right? In Korean. Minimum clock period. So this clock period supposed to be T, supposed to be 950, right? 950 picosecond. Clock period supposed to be equal or bigger than this number for single cycle CPU to operate properly. If T is less than this number, what would happen? If T, let's say T is 800 picosecond, let's say. What happens is this. Let me draw clock. Okay, let's say this one is minimum required clock period 950. Let's say this one is 950, and somehow you are providing this clock, which is like this. I'm drawing. Let's say this period 800. And then the thing is, at the rising edge of the clock, register file is trying to update. What data? Data is not available, right? Look at this mem data. I removed it almost, but this mem data is not ready yet. So at the rising, this dotted line, right? At the rising edge of the clock, you are trying to update this unknown, some garbage data to that memory, to that register file, to register location X5, right? So data is not ready yet. So if the clock is shorter, clock period is shorter, then CPU is not operating properly. You are updating garbage data to register file, right? That will be disaster, right? So that is a minimum. So longer is okay, right? If the clock period is longer, for example, clock is running like this. Clock period is longer like this. Okay, at this point, right? You are trying to update, right? So data is ready long time before this rising edge, right? So data is ready, no problem, right? But shorter, then CPU is not working. So minimum. So then if you want to get clock frequency, right? F is what? Frequency is 1 over T. 1 second. In other words, 1 second. In 1 second, how many T? How many T's? How many clock, right? How many clock period you have? How many T's you have? That is clock frequency, right? Within 1 second. Within 1 second, how many T's? How many T's you have? That is clock frequency. So if you plug that number into that equation, 1 point, roughly, 1 gigahertz, roughly 1 gigahertz. That means in Korean, 10억 T's, right? 10억 T's here in 1 second. 1 billion clocks, 1 billion clock cycles, 1 billion first clock cycle, second cycle, 1 billion clock cycles you have in 1 second. Okay. Okay, so we haven't talked about this equation, so let's just skip this part. Okay, that is concluding single cycle CPU discussion. Any question? If you don't have any question, we are moving into pipelining. No question? Okay. Okay, so let me show you some demo. Okay, let me show you some simulation demo. Because you are probably new to hardware design, so better to show you some examples, right? So last time I briefly showed you model simulation. Okay, so let's start from the beginning. You have to prepare first the milestone, right? You have to prepare MIF, memory initialization, file, because why? Because what? Because our memory, right? This memory is demanding that MIF, right? Memory initialization, right? Memory initialization, okay, MIF, that file. So you have to provide MIF, okay. So as an example, okay, so this is a lab milestone number 3, okay, 7 sec. Here, let me change the code, simple code first. So what would be, what instruction do you want to test? Addition, okay, simple, right? X3, X0, then 12. Then next instruction, sub instruction, okay, X4, X3, the one you just updated. Then sub. Okay, one more addition. Okay, add X4, X0, prepare, right? Some 4 about that. The next 5. Okay. Then 4, X3. How about that? So you are updating 3, 4, then taking that output and doing subtraction. So 4 minus 12, minus 8, right? Some numbers supposed to be saved. Let's just test this. And one more, BEQ, about BEQ. BNE, X3 is equal to, not equal to, confusing, right? Equal to X4. Then go to 7 sec. It does not go, then not equal, right? Then that is taken, that will be taken. X3, X4, 12, 4, right? 12, 4, not equal, then go to 7 sec, which is that function. Okay, so let's test, okay, that code. Compile it. Okay, MIF generated. You have dump, check out, right? So location, memory location 0, you have that machine code. Okay, so that got changed to that pseudo instruction. It doesn't matter, right? That will be addition instruction. 4, 8, then so on. So 7seg is located at 20 memory location. This label location memory 20. Okay, location 20. Then so let me test with that solution, right? So I gave you the solution. Okay, hardware design. There is a solution. Okay. So for simulation, you have to place that MIF to that folder. Overwrite. Okay. MIF got overwritten. November 10th, 11, 19. Okay, just now. Then run model sim. Okay. Change directory to that place. This place. File. We'll change directory to that place. Can you do this? Copy, paste. Oh, not sin. Okay, not simulation, right? Simulation, sim directory, sim. Sorry. So I'll do it again. Clean it. Build. Okay, MIF got generated. That should be copied to simulation, right? Simulation directory. Okay, so that, can I do this? Change directory to that. Okay. Okay. Then this work folder, right? This is the place I compiled. Compiled what? Compiled all this hardware design. This all hardware design, right? You have to compile first, Verilog design to make sure you don't have any syntax problem. Syntax, okay? And keyword problem, right? Then go to work, then test bench. That is the test bench, right? This one, TB, okay? RB32i, TB. So module name, RB32i, TB, that name. So right click on it, simulate. Okay, then you have to figure out what signal do you want to observe in simulation, right? So obvious thing is, let me show you data path. Okay, so obvious signal you want to observe, those things, right? Pro and counter, instruction coming in, and source operand properly prepared, ALU output, then mem output. Those signals probably you want to observe, right? So you have to check here, CPU, okay, and clock reset. Those are default, right? Clock reset, default signal you want to add. Reset, pro and counter, instruction, probably memory write control signal. How do I know? Because I designed it, right? I designed hardware. So click on this. So we are talking about the CPU, iCPU. Why iCPU? Instance name, right? Look at this system. Search iCPU. Yeah, right. Instance, right? This module name, actual name, but instance name, right? Instance, iCPU, instance. You are instantiating. You can instantiate many CPUs, but first CPU, I want to name it iCPU. Okay. So inside that iCPU, those control signals, probably memory, by looking at this, memory address, right? So add those to wave. Okay. You can add everything, but if you add everything, confusing, right? Too many signals to, too many signals. So try to add some signal of your interest, right? So you have to check out the register file to for that source OP1, source OP2, ALU inputs, right? So you have to check out Verilog design. So data path probably. That is in data path. Data path. Go down. And we have a register file here and ALU. Right? So you want to see, you want to observe this one. ALU source 1, source 2. Right? So from here, data path. From here, data path, we have what? ALU source 1. Where is that? Data path, ALU, data path. Okay, here, ALU source 1, ALU source 2, then probably ALU control as well. So add these two first, add to wave. Okay, then ALU control signal, add to wave, then ALU out, right? Output, this ALU out, add to wave. Then memory data, okay, the data. So in this sequence, I don't have to. In this example, probably I don't have to. Okay, addition, branch. Okay, so I don't want to add memory access related signals, right? So what else? So I just added source 1, source 2, ALU out, PC, instruction. Then probably you want to observe register file, right? Because that instruction, right? That instruction is updating X3, X4, X5, those things. So you want to figure out, you want to check out, right? So where is the register file? Okay, so let me close too many. Test bench, let me close. Okay, so register file is here. You can observe everything actually about register file because we designed it with register file. Okay, register file is where is the register file? Go to here and CPU basic modules, right? So here we have reg file, register file. So you can observe everything, right? X1, X2, those signals, right? Those registers, sorry, those registers. So you can go into here, you can go into reg file, right? Reg file. Then we have everything, right? So check out let's check out X1, X2, X3, those, those registers. Okay, add to wave. We just added X3, 4, 5, 6, 7. 3, 4, 5, right? 3, 4, 5. Okay. Okay. And X0 also. X0 is not, 0 hardwired, right? So then the run simulation, right? I think that is just enough for our test vector, test vector, that test vector, right? So you want to test those, those vectors, right? We call that test vector in hardware design world. Okay, for these test vectors, I think those signal would be okay. So then run simulation, run 10,000 nanosecond. So let me make it full. Okay. Full screen. Oh, that is full. Not full, right? Which one is the full? Okay, this one. I'm confused. Bit. Okay. So reset, right? Reset is high. Okay. Let me zoom this one. And this binary, I don't like binary numbers. It's confusing, right? So change radix to hex. Okay. Okay. So reset goes down here. So starting from, okay, I don't have to keep that big. Oh, so everything is gone. Okay, so okay, so here show you that Eclipse dump is enough. Compare that. So first machine code 00C0 193, right? The first one. Look at this. Location 0, right? The one right below, right? 00C0 0193, right? First instruction. First instruction. And oh, I okay. So and then four, location 4, right? Location 4, 213, right? 213. This one. And location 8, 2B3, right? 2B3. This is doing instruction patch, right? Correct. Then first instruction is updating what? X3 register, right? Look at this. X3, the register. Okay, so at the rising edge of the clock, so it is updating a long time before because the reset, sometime before. So during reset, some hardware is not perfect by design. Toy, hard CPU example. So even though it is a reset period, X3 is updated. Okay, register file is not taking reset signal. Remember our register file design is not taking reset clock, only clock, right? So because of this toy example, right? Toy example, even though it is a reset period, you press the button, reset button here until this time, it is updating, this one. But it doesn't matter, it's okay. It is functionally okay. So the thing you have to see is right after reset, right? Right after reset, instruction get executed. First one, okay? And second instruction is updating X4. It is okay now, right? X4 is updated at the rising edge. It's the rising edge of the clock. Okay. Instruction patch to execution. Patch to execution. And X5 is updated, right? X5 that is updated here. Okay. X5. So what is X5 updated with? This value. 7 Fs and 8. 7 Fs and 8. Right? That is correct, right? We are talking about what? We are talking about that code, right? First one, X3 is X3 will be 12, X4 will be 4. Then next instruction, right? Subtraction instruction, X5, 4, 3, right? So 4, 3. So 4 minus 12 supposed to be minus 8. So if you so what is minus 4? Minus 8. In computer, right? So 2's complement notation, right? So if you do the math, then that will be 7f's and 8. 7f's and 8. Starting with 8, then you do flip all the bits, right? Then add 1. So you will get this one. So there is 1. Then next instruction is branch, right? So branch instruction supposed to what? So 7sec program counter should be updated to that value 20, right? So if you look at this, instruction C, right? Location C, branch instruction. Location C, branch instruction. Okay. Too small, right? C, branch instruction. Then what? 1, 0. Why 1, 0? Jump instruction and 20. PC 20 here. 1, 0, 20. So branch is taken, right? So my thinking is this reference CPU has a bug, right? C next one supposed to be not 1, 0, right? Is it correct? I'm confusing. Isn't BNE, BEQ? BEQ? It's correct. Is it B, right? Let me check. BNE. Okay, I didn't save it? Why BEQ? Why BEQ? Okay, let me compile it again. Nothing. Clean project. Okay. Guild. P. Oh, okay. That is correct, right? Okay. So I know. Okay. So that instruction translated into these two, right? These two. Okay. Compiler compiler decided to use BEQ instead of BNE, right? So equal, then go to 14, location 14. 14. Otherwise, you fall through. That means jump. So correct, right? So here, okay. So C branch instruction BQ and 1, 0 jump instruction. Jump instruction is updating program counter to 20. So 20. PC got 20 here. Executing 20. That addition instruction. FE something, right? This one FE something. Right? So probably in addition to this data path, you have to observe also control signal, right? So important control signal is this register write. Okay, you have to check this register write. Somehow your hardware design does not update register file. You have to check out this reg write. Okay. So where is reg write? Register file, right? Either this one, write enable, or go to data path, reg write. this one probably add. So that signal is not, the data is not shown. You have to restart simulation to see this one, to see the signal. And PC probably, program counter. How about that? Because we are executing branch instruction, right? So here, branch destination, branch destination. About that, branch destination, JAL destination. How about branch destination computation? Where is that? Is it data path or data path, right? Data path. So inside data path, branch destination. That is, I want to see branch destination. Okay, and also selection signal, right? Who is updating program counter PC based on be taken or JAL? Those things, right? Be taken. Let me check out this be taken. Branch taken control signal. Be taken. Where is that? B. Okay. BQ taken. B taken. Okay, here. Branch taken. And you want to check out this JAL also. Okay, here, these two. Add wave. Okay, so now we have added some control signals. So you have to restart the simulation. How to restart? Simple, restart, right? Restart. Type it. Okay. Then run simulation. 10,000 nanosecond. Okay. So we have a new simulation result. So now I want to change everything in hex. I don't like binary, right? So check out this. The beginning from the beginning. Get this. We want to zoom. Zoom. Here. So check out the last instruction brand BNE instruction, which is converted to BEQ and jump, right? So jump, right? Program counter is changed based on that instruction, right? Jump. So jump instruction is located at 10, memory location 10. Okay. So this one is jump instruction 6F. Okay. Then look at this. This control signal JAL. Control signal is asserted. That control signal is asserted. JAL, right? JAL. Control signal is asserted here. JAL. So at the rising, so that is why at the rising edge of the clock, okay, according to that description, Verilog description, if look at this, branch be taken is 0, right? Branch taken is not asserted, be taken, and JAL is asserted, right? JAL is asserted here, 1 to 1, okay, to here, right? So that is why program counter is updated with JAL destination. Oh shoot, I didn't put JAL destination. Let me put JAL destination. That signal. JAL destination. Okay. One last. So J. Okay, this one. Add to wave is shown. So restart and run 10,000 nanosecond. So that is in decimal. So change that to hex. Okay, we are interested in first few instructions. Okay, so here now, okay, zoom in some more. Okay, so JAL destination. Look at this. JAL. So rising edge of the clock. Rising edge of the clock. Okay. JAL destination is 20. So it looks like it is changing. It looks like, okay. It looks like JAL destination is changing to some value at the rising edge, right? But because it is simulation, you can add some delay. JAL destination, okay, is computed. But in the real world, right, you have to differentiate two things. You have to differentiate two things, functional simulation and timing simulation. Two things, functional simulation, and second, timing simulation. And we are doing this. We are doing functional simulation. Okay. So if you don't say anything about delay, so here, below description, you didn't say anything about the delay. But here you said, okay, delay. Assigning is taking some amount of time delay. But here we didn't specify anything. So that means functionally, simulator is doing addition without any delay. Without any delay, just add, then assign to that signal, that wire. Okay, that is why the delay is not clear. This delay is not clear in functional simulation. But after you translate Verilog into actual hardware, AND gate, OR gate, flip flop, right? Then after that, you are doing timing simulation. So in this class, but we are not doing timing simulation. So you have to be careful, right? It looks like it is changing. So you are taking picture, but it is changing, right? Then what would happen? But because we are doing, right? So rising edge, some little bit of delay, but it looks like changing, right? So you have to be careful, right? You have to be careful. So at the rising edge, you are updating 20. Jump destination to PC. Look at this, PC. PC got changes to PC. Program counter. PC got changes to that, that jump JAL destination. Okay, at the rising edge. A little bit of delay because we specified the delay. Program counter will be updated after a little bit of delay, right? That is simulation, how you run simulation. All right, any question before letting you go? All right, that is for today. I'll see you next time. Okay, bye. Okay. Okay, question? Milestone 3, 4. 여러분 마일스톤 넘버 4는 아마 오늘 시작하기가 어려울 것 같아 좀. 그렇지? 아직 그 파이프라인 얘기를 전혀 안 했잖아. 그래서 아마도 듀를 조금 더 늘려줘야 될 것 같은 생각이 드네. 일단 조금 어그레시브하게 잡았긴 했거든. 여러분이 근데 그럼에도 불구하고 좀 생각을 해봐. 4가 이게 이제 제일 어려운 고비거든, 여러분. 한 일주일 동안 잠을 안 자는 학생들을 본 적도 있고. 이게 고비니까 여러분 미리 좀 생각을 하되 생각을 해봐 여러분들이 미리 생각을. 근데 요 듀는 조금 늘려줄 거야. 요 듀는 너무 좀 얘기를 안 해서 아직. 오케이. Okay. Any other questions? 혹시 수요일은 17일인데 17일? 아, 그러니까 17일? 원래 오케이. 원래 17일이었구나. 17일이었는데 잘못 썼네. 근데 듀를 17일 말고 좀 더 늘릴 것 같아. 당연히. 이거 너무 좀 촉박하네. 강의를 하고 여러분이 감을 잡은 다음에 좀 해야 되니까 뭐 금요일 혹은 뭐 월요일 그 정도로 듀가 되지 않을까? 20일 혹은 22일 뭐 그 정도. 근데 생각을 좀 해봐요, 여러분. 오케이? 미리 좀 생각을 해봐야 될 거야. 시뮬레이션도 익숙해져야 되고 다 시뮬레이션으로 버그를 잡는 거기 때문에. Okay, any other questions? Okay, see you. Bye.